Hello everyone, I am Ganesh babu. I am going to explain speed estimation methods of induction motor. What is induction motor? Induction motor is a device which converts electrical energy into mechanical energy. It works on the principle of electromagnetic induction. It is classified as single phase induction motor, three phase induction motor, synchronous motor, and special purpose motors. And they have many industrial applications because of rugged, reliable, and economical property. They have self starting property and high power factor. Speed of an induction motor. Synchronous speed of an induction motor is nothing but induced magnetic field in the rotor is matched with magnetic field in the stator. At that time, one speed is produced and motor will rotate. That speed is called synchronous speed, and the synchronous speed can be theoretically calculated by using the formula ns is equal to 120 into f by p. Slip is nothing but it is the ratio of relative speed to the synchronous speed. Before we going to know about the speed estimation techniques, we must know about rotating magnetic field concept of an induction motor. For this, we will see and I will show you one animation video. It will helpful for understanding the further slides.
Three-phase AC motors, whether synchronous or induction, are robust and designed for high power. That's why they're one of the most commonly used electric motors. So what is the basics of these three-phase motors? It is all because of the rotating magnetic field generated by the motor winding. To understand RMF, have a look at this single wire connected to DC. The concentric magnetic field can be determined by the right-hand rule as shown. Connecting the wire to AC. Since the current is alternating, the magnetic field also varies in strength and direction, but still is not rotating. To get to an RMF, you need three wires, which are rotated 120 degrees to each other and connected to three-phase current. Magnetic fields with same direction can be combined as you see. This makes our illustration much simple. Let's start and make some snapshots to see how the RMF rotates. Now, the magnetic field rotated 360 degrees with same strength within a complete period of the input signal. Consider that this magnetic field has just two poles. The question is, how is it possible to vary the speed of the RMF? With this arrangement of the wires, we now have four poles. Let's start the animation one more and watch the speed of the RMF. What you can note is that the speed of the magnetic field has become the half. The speed of rotation of this magnetic field is known as synchronous speed. In general, the synchronous speed is given by this equation. Concerning the technical implementation, the stator consists of a hollow, cylindrical core with a number of evenly spaced slots, which provide the space of the stator winding. To interrupt the path of the electric eddy currents, this core is made up of stacked laminations. Watch also our next videos.
In this video, above video, we all see the rotating magnetic field concepts. Let us skip through speed estimation methods. Speed estimation methods can be classified into rotor slot harmonics, frequency signal injection, and MM-based method. In MM-based method, Kalman filter, adaptive observers, SMO, AI methods, and MRAS methods are there. Rotor slot harmonic method. In this method, speed is estimated by detecting the space harmonics induced by the rotor slots. That rotor slots produce harmonic components in the air gap, a magnetomotive force that modulate the stator flux linkage at a frequency that is proportional to rotor speeds and number of rotor slots. And the output voltage is the sum of input voltage, one third of the sum of input voltage. Block diagram of rotor slot harmonics method. explains. And the adaptive bandpass filter extracts the rotor slot harmonic signal. The filtered signal is digitized by detecting its zero crossing instance. A software counter is incremented at each zero crossing by one count to memorize the digitized rotor position angle. A slot frequency signal is then obtained by digital differentiation in the same way as from an incremental encoder. The accurate rotor speed is subsequently computed with reference to equation. Next, next one is free FSI method. FSI means frequency signal injection method. In this method, an estimated field angle is used to perform the current control in field coordinates. A revolving carrier frequency is injected through the voltage signal. The carrier frequency components is measured. Machine currents are attenuated by a low pass filter in the feedback path of the current controller. A band pass filter extracts the carrier generated current vector IC. The rotor speed can be estimated by using phase locked loop. Speed estimation scheme in this method is based on signal injection. Direct calculation method. Next one is this is come under machine model methods. First one is direct calculation method. In this direct calculation method, speed is calculated by using the above formula. Omega r is equal to 1 by lambda r square lambda drs lambda qrs minus lambda qr lambda dr minus lm by tr lambda dr I square iq square lambda qrs I ds. Lambda r means nothing but rotor flux vector. Lm means mutual inductance. Tr means rotor time constant. And lambda cap means estimated rotor flux vector. Okay, we can estimate the speed by using the direct formula. The values are given, we can estimate the speed of an induction motor. Next one is MRAS method. MRAS method means Model Reference Adaptive System. The MRAS speed estimation structure basically consists of reference model, adjustable model and adaptive mechanism. The reference model, which is independent of the rotor speed, calculates the stator variable X from the terminal voltage and current. The adjustable model, which is dependent on the rotor speed, estimates the stator variable X vector. The error E between calculated and estimated static variables is then used to drive an adaptation mechanism which generates the estimation speed omega r vector for the adjustable model as shown in the block diagram. It should be noted that speed estimation method using MRAS can be classified into various types according to the state variable. The most commonly used are rotor flux based MRAS, back EMF based MRAS and stator current based MRAS. In rotor flux based MRAS, the rotor flux is used as an output value for the model to estimate the rotor speed. When the rotor flux of the adjustable model is in accordance with the reference model, the rotor speed of the adjustable models represents the real motor speed, and the estimated rotor speed can be calculated by using the above formula. Next one is back EMF based MRAS. The open integration is circumvented in this approach. Other than in MRAS based on rotor flux, there are no low pass filters that create a bandwidth limit. The back EMF is calculated from the reference model based on the terminal voltage and current, where E vector is the back EMF estimated from the adjustable model, and the speed is estimated by using the given formula. The next method is stator current based MRAS. Stator current may be used as an output value for MRAS speed estimation model. The rotor speed is estimated according to this method using the rotor flux, which is expressed in terms of stator voltage, stator current and motor parameters. And the speed is estimated by using the above formula. We can find out that the rotor's error of an rotor speed can be written as omega r minus omega r cap vector, whereas n is given by the Lm by Tr into 1 by lambda dr square plus lambda qr square. Next one is KF approach. KF means Kalman filter approach. This is suitable to the system which has many unknown noises such as current ripple by pulse width modulation, noise by modeling error, measurement error, and so forth. These noises are treated as disturbance in Kalman filter algorithm. In real systems, some uncertainties in the model and environment as modeling inaccuracies, disturbances, and noise should be considered. In this block diagram, the inputs to the plant are fed into a prediction model. The output of the plant is compared with the output from the model, and the resulting error is fed into correction Kalman gain stage to reduce the error in the estimated states from the prediction model. The Kalman filter approach has some inherent disadvantages such as influence of computation burden, the absence of design and tuning criteria. It is relatively complicated and requires much more powerful microprocessors. The next method is adaptive flux observer. Adaptive flux observer are also used for speed estimation of induction motor drives. The structure of an adaptive observer is basically composed of three main parts: an induction motor model, observer's feedback gain, and rotor speed adaptation mechanism. The characteristics of speed estimation is governed by the assignment of the observer's feedback gain and PI gains adaptation mechanism, and the speed can be estimated with the help of given formula. The feedback gain K is chosen to ensure global stability, robust dynamic performance of the closed loop observer. A pole placement approach is employed, and the choice of desired pole locations is usually a compromise between achieving faster response and retaining high robustness. The adaptation gains are selected by trial and error or by considering the root locus of the linearized model. These methods based on machine models stated earlier execute accurate and robust speed estimation performance. These methods may achieve robustness and high performance with parameter variation. The final approach is artificial intelligence technique. The use of artificial intelligence to identify and control nonlinear dynamic systems has been proposed because they can approximate a wide range of nonlinear functions to any desired degree of accuracy. Moreover, they have the advantages of immunity from input harmonic ripples and robustness to parameter variations. Recently, there have been some investigations into applications of AI to powered electronics and AC drives, including speed estimation. Two well-known voltage and current models for the rotor flux are necessary to estimate the speed of an induction motor using a neural network. Since the induction motor voltages and currents are measured in stationary reference frame, it is convenient to express these equations in stationary frame. They are expressed in terms of state equations. The voltage equations that do not involve is defined as the reference model. The current equations involving omega r is defined as the adjustable model. The output of artificial neural network is defined as the estimation speed, which is subsequently used as the input of the adjustable model. If the estimated speed deviates from the real speed, an error occurs between the flux from the adjustable model and the flux from the reference model. The error is back propagated to the artificial neural network, and the weights of neural network are adjusted online to reduce the error. Finally, the output of neural network follows the real speed. Okay, these are all the above techniques that will useful to estimate the speed of an induction motor. Thank you for watching the video. Thank you.